Welcome to the final presentation of the day. I'm Amit, and Amiraj, unfortunately, is unable to join me on stage today. But what I'll be presenting here is a small part of an exciting journey that we both kind of shared together in the last couple of years. As is customary, we'll first take a commercial break. Yelp. It's all about connecting people with great local businesses. End of commercial. Let's get back to the talk. All right, here's the outline of the talk. So we'll be covering enough background and context just to make sure that you're able to get a sense of the, understand something from the talk. So given the wide possible, the spread of the audience and how much they may or may not be aware of in terms of Spark or Kafka or Cassandra and such. We'll talk about the business requirements that motivated and drove this work. Some design iterations we went through before coming up with the exactly one solution. And finally, close with some remarks on ongoing work as well. So this work was actually done within the context of local ads. So here's some background in there. So we kind of manage about a few 100,000 campaigns on a daily basis. Ad campaigns, and they range from mom-and-pop stores all the way to national chains, like say Starbucks. So what we'll be presenting today is in the context of data processing pipelines that receive a few thousand messages a second, and these pipelines have been in production for more than a year. I mean, the first one was way more than a year. So definitely, it's been in production for a while, and there are multiple of those. All right, so to get some context and set up enough background to get the business requirements here. So let's say a business decides to advertise on Yelp, and the next one is a snapshot of the Yelp app, and a user performing a search may see related ads above the organic search results. Now, if the user, when they view the ad or they happen to click on an ad, maybe they call the business related to the ad, or they actually check in there. Now, all these events are logged and produces a log stream containing all these events. And this log stream then gets either processed on a nightly basis through Hadoop jobs, or is running through around the clock, day and night, Spark streaming jobs. But this processing eventually, directly or indirectly, leads to reports for the business that's advertising. Also, they get to see how their campaign's performing on a business-specific app that also is a Yelp product. And then eventually, of course, invoicing, billing, stuff like that also happens via the output of these jobs. Now, what's more relevant to this particular presentation, though, is the stream processing side and how it powers the management of ad campaigns. So some examples here are trends, the campaign trends, how they're doing, the setting up of bid prices. So ads usually are kind of in an auction system, and the best ad is picked based on the bid prices. And so the bid price setting, and also personalized targeting. So these are some examples of Spark streaming or streaming in general, kind of enabling the various functionalities behind the scenes for an ad campaign. So given all these use cases we just spoke about in the previous slide, we wanted a general solution that could aggregate events over a day period, slice these aggregates along predefined dimensions or keys, as you may also consider it to be. And these would be defined by the end use case. So depending on whatever the use case is, the dimensions would basically be determined by those. We also want to provide partial aggregates as the day progresses. And finally, make these aggregates as accurate as possible, because, again, we're dealing with multiple use cases, so they may have different requirements. So let's make this a little more concrete with a simplified example. So let's say you want to actually count the number of ad clicks over a day period, provide these click counts by an ad campaign, and finally, continuously update these click numbers as the day progresses. So in the figure at the bottom, we have snapshots of the same table over time. So in the first case, at a certain time in the day, let's say we had 35 clicks reported so far. Sometime further down in the day, we may have 42 clicks for the exact same campaign on that same day. So this is the kind of behavior we're actually expecting from this system. So essentially, the numbers keep getting updated, and that way, downstream systems can actually act on those numbers. So what's the tool set do we have to solve such a problem? So on the left, we have one or more data streams, which could be, well, at least some prominent examples are Kafka, which there was a whole lot discussed in the last talk. And then Amazon Kinesis is another example there. In terms of the stream processing engines themselves, again, Spark streaming, but also Flink are some solutions there. And then on the output side, we could either be emitting new streams, or we could be putting data into a database, typically a key value store. And again, examples there could be Cassandra or Redis. And there are, of course, way many more. It's a much crowded space, but just a few examples that I have here. And in terms of what we use, or at least in the context of this particular talk, we're going to kind of stay focused on Kafka, Spark streaming, and Cassandra on the output end. Alrighty, so one more thing before we kind of actually talk about a solution is the windowed operations, the idea of windowed operations in stream processing. So at the top, you see a tumbling window, which is kind of where data is. So I should maybe mention first that, yeah, in general, stream processing, you have like events coming in, and there are definitely a lot of use cases where you're just processing one event at a time in a stateless fashion. But the more interesting use cases are typically where you're actually doing operations over a window of events. And so a tumbling window would be where you have non-overlapping windows of time, like the example we were talking about, I mean, aggregating over a day window, for example, where each of these could be a day boundary, and then we're trying to do some kind of aggregation or whatever operation within that context. There's also other kinds of windows, sliding windows, another example where they're actually overlapping windows of time. There's also like session windows, which are like session-based, for example, user sessions. So there are definitely multiple kinds of ways you can window things, but for the purposes of what we're going to talk today, tumbling windows is all we care about. All right, so back to our original problem. We wanted to count clicks over the period of a day. So why not we just do this? Why don't we just kind of take this stream in? We just talked about tumbling windows. So we just kind of bucket it over a day window, and then have this processing pipeline just produce this final sum on the other end, the number of clicks. So why not just go with this? Well, basically, two things. One, of course, is the fact that tumbling windows don't produce anything until the end of the window is reached. So it's kind of a stateful system. It's kind of internally aggregating your data. And then finally, when the window is done, is when you have the final number. So that's when it emits the output. So clearly, the requirement we had was, oh, we need to kind of see partial aggregates as the day proceeds, which means, in this case, that's not going to work. We're actually going to be waiting till the end of the day before we get a number. We might as well have just gone with batch processing at that point. All right, so how about we don't depend on that, but instead kind of just take in a bunch of events, do just aggregation within the scope of those events, a lot less. I mean, so we're not talking about day window anymore. Let's say a few minutes or maybe even seconds, whatever. Aggregate just whatever we just got in, and then kind of let the database take care of the deltas. So essentially, we send an increment, and then on the database side, we just basically have it do the work of aggregating and keeping the final state in there. And that kind of was something we looked into, which kind of looked promising, because Cassandra does have a data type called counter, which is an integer type. It can do increments and decrements, and so it seemed like, OK, maybe this could work. But digging a little more into it, we found out that it's actually not meant to be idempotent. So it's great for approximate metrics, like likes, follows, stuff like that, but not so much for when you want to have higher levels of accuracy. I mean, so we did talk to DataStax, the company behind Cassandra, in many ways, and they actually reported as much as 5% discrepancy in terms of just what they've heard from the industry at large. And a lot of the this also is case-driven. I mean, the discrepancies are a result of the distributed nature of Cassandra and how things propagate across the cluster. And also the 5% or up to 5% is really a result of how you use it as well. So it's not really a single defined way or a single defined bound on what discrepancies you might get. And finally, they also mentioned that they have no plans or roadmap at all in terms of making it idempotent down the road as well. So it was not something we could kind of wait for and then kind of improve our accuracy on. Alrighty, so this is what we came back to. So okay, so it doesn't look like we can use tumbling windows. It's not like we can use Cassandra and leverage any kind of increment like operation on that side. So what we could potentially do is kind of take care of the incrementing within the processing pipeline and then publish back the final result. So essentially, read in the current value. So use Cassandra as the current as a state for keeping the current counts, and then do the increments for the new data that comes in, and then publish it back to Cassandra. So that way, you're kind of doing the work in the processing pipeline, but you're keeping Cassandra as a way to kind of keep that state, track the state. So what does that look like in terms of actually doing a pipeline? So for that, let's just quickly go over a few one-on-ones, and then we'll jump into, OK, what would it look like from a pipeline perspective. So you've heard a lot about Kafka in the last talk, but that was more on the architecture, or more on the operational and infrastructural side of things. This is more on the application layer. So this is just a one single slide quick review of Kafka. And this is all we really need for the purposes of this presentation. So Kafka, the data is organized or partitioned into partitions. And each partition has a notion of an offset. So data in the partition is ordered, and they have a well-defined offset, kind of an index into that particular data block. And the consumers who consume this data have to kind of keep track of their own progress, meaning if a consumer is consuming from, say, the first partition, if they read as far as offset 4, and the next they want to read offset 5, in the information about how far they've progressed on that particular partition is something it's the consumer's responsibility. But Kafka does provide ways to actually persist that information, so the consumer can actually send that or commit that offset to Kafka, and Kafka will hold it for you, but it's still your responsibility to do that work. Alrighty, so that was Kafka. And then the other piece we wanted is Spark streaming. Here again, single slide, just the basics that we need for this particular talk. There's, of course, a lot more to all these systems. So let's say we have these streams coming in. There's processing going on. The way it works is traditional Spark streaming, you do micro-batching, meaning something like you tear out a stream, a few records from on the front of the stream, you process that. And then once you're done with that, then you can, again, tear out the next batch and then process that again. So there's no pipelining, meaning that you completely process the current micro-batch before you start processing the next micro-batch. And even within the pipeline, if you had multiple stages, again, there's no pipelining, meaning stage 1 will completely finish processing, and then stage 2 will completely finish processing, and then stage 2 will start and finish processing. So there's no parallel execution of multiple stages going on internally. And finally, the app basically has to manage the offset commits. So back on the previous slide, we were talking about how the consumer has to take care of the committing of offsets. So it's the same deal here. It's just that the Spark streaming layer doesn't take care of it, or at least in this context, the best guarantees are provided if the app basically manages the commits. So the app has to keep track of how far it's progressed, and then essentially go back and commit that information wherever to either to Kafka or whatever data store it wants to use. So all right, so we have the tools. So let's kind of put these two together and see what it looks like, what a system might look like based on the idea we came up with before. So on the left, you have the data stream kind of coming in. We kind of tear off a micro batch. And then stage one, essentially what we could do is aggregate just the information. So in this case, clicks. We just kind of add up all the clicks for a campaign as part of the first stage. And then stage two is going to receive the dimensions or the keys. Like in this particular case, it would be the campaign ID and then the day as inputs from stage one, so that stage two can actually get that information for the current count from the database, from Cassandra. And then finally, in stage three, we would have the current state. We would also have the increment that we wanted, and then we combine them. And then that way, we can publish it back to the data store. We would have the new value. And then at the last, like once these three stages have succeeded, finally what we could do is kind of commit the offset based on how far we made progress. So this particular microbatch, let's say it took first 4 records out of the stream. So we have successfully processed that. We have the updates in Cassandra, so we can basically do that commit. So then the next time we read in, we're basically going to start from offset 5. So looks good so far. Are there any problems? Well, like to kind of quote Ken Arnold here. Of course, it's a very dense slide, but just the highlighted regions is basically the point here. It's that distributed systems, it's all about failures. So that's what you design for, and that's kind of your primary concern. So, and it's a distinguishing factor between local programming versus distributed programming. So you're always kind of looking for the failures when you're kind of developing for the distributed world. All right, so let's see what it means in terms of failure modes. All right, so what happens if stage 1 fails for whatever reason? So let's say we kind of either throw an exception, and then we fail stage 1. Spark basically has this retry on stages, and so you can basically configure that. So it'll retry that particular stage. But in any case, I mean, stage 1 is really doing reads. There's no side effect. There's no real writing going on. So it's essentially safe. So stage 1, if it kind of fails, retries, it retries horribly, and then the whole application restarts, no problems at all. Stage 1 is good. All right, what about stage 2? Stage 2 does read from the database, but again, there are no side effects, nothing at all. And then there's no pipelining, so unless stage 2 succeeds, stage 3 is not even going to start. So there's no side effect again, no problems. Stage 2 is good. All right, so stage 3, things get a little interesting. So now stage 3, let's say, starts writing to the data store and then fails somewhere in between. And so some of the records in the database have been updated. So some of the campaigns have updated clicks, while let's say the rest of them don't. And then let's say the whole application crashes at that point. Now, when the application restarts, we did not do any commits for the ones that were successful. And so we're just back to wherever the offsets were in the previous microbatch. So we're going to re-ingest exactly the same data, or at least all of the data from the previous microbatch, and then go through these processing stages. Except the problem now is that the records that were updated, now stage 2 is going to get those updated values, and then the same data is going to come in, and there's nothing to distinguish between the two, and so it's going to actually increment it again. So we're going to basically increment those values twice before committing back to stage 3. So essentially, we have overcounting at this point. And also, the failure mode on the last one where we do commits is, again, the same in the sense that if we didn't commit and the application fails at that point, we are again going to re-ingest data from the previous microbatch. And in this case, we did not, we're going to double count everything because we essentially committed everything in the previous microbatch. So what it comes down to is essentially we have failure modes where we're going to overcount and not really get the right counts. So one aspect is that we saw that there were only like failure modes where we were overcounting, like we were never undercounting. So that's kind of a good thing. I mean, essentially, we're always kind of erring on the side of re-ingesting data that we have already either processed or not processed, and hence we're always going to get the data and never miss out on data. But on the other hand, like we are going to be overcounting in some cases, some failure modes. So how do we go from that to achieving exactly once? So here's kind of the basic observations in terms of coming up with that solution. So one thing is we are clearly not able to distinguish between processed versus unprocessed data, and that's basically where the overcounting is coming from. One way to look at it is like, okay, if there is a way to kind of version our aggregates or our the sum data, then we could figure out a way where the same data comes back in. We are like, oh, this still belongs to the old version. We don't have to count this. So versioning kind of is a way, or at least we could come up with a strategy which kind of looks like versioning to achieve this. And of course, one thing with versioning is that, oh, they're always monotonically increasing. Like your versions always go up. But at the same time, the nice thing is that Kafka partitions, data is already ordered. They have a notion of offset, and they are also incrementing all the time. So if you can combine these two aspects, we can come up with a solution. And in fact, that's what we did. All right, so let's see what that looks like. So here's an example. We're just going to take, let's say, one particular ad campaign, ID 5, and we're going to take click data. So if there's a CLK in a particular event, which means that we did get a click. If there's nothing, that means we didn't get a click on that particular event. And the table, of course, looks like before, except for the extra column now. So we have a column called version, and let's see what we do here. So we take the data, we process it, and then once we are done with processing, we take the highest offset corresponding to data that we've already processed, and that's what becomes the version. So in this particular case, campaign is 5, ID 5, and then we have 3 clicks at the time where we are offset 2. So the number of clicks is 3, and then by then, we basically are saying that, oh, OK, version is 2 because we have processed as far as offset 2. Now, for whatever reason, if you're unable to commit this, so we process till offset 2, we're unable to commit, the application crashes, comes back up, we re-ingest the same data. You're going to have offsets 0, 1, and 2. But when you read the current state from Cassandra, you're going to have version 2 coming along with it, which means that we can now kind of discard the data 0 through 2 because the version is 2, and we already processed till 2. So we only process data that's higher than the version, like the offset's higher than the version that we've already processed. So of course, we may have more than one row or campaign ID, so we have to maintain this version on a per dimension or primary key basis. So in this particular case, we are again processed till offset 2, but as far as the ID 9 is concerned, 1 is the highest offset that we have processed so far for that particular campaign. And then for ID 5, yeah, we've gone basically to offset 2. And so the version is based on the highest offset that we have processed for a particular key, or for a particular primary key combination. So that's the basic idea. Of course, the other thing is that, yeah, there might be more than one partition. So it's not just a matter of one number as far as the version is concerned. So on a per primary key basis, we also want to kind of track which partition and what the offset is. So essentially, that's the idea as to how we keep track of versions and how we can kind of avoid overcounting. So what does it look like as far as the pipeline is concerned with this modification? Well, things have moved around a little bit. So now stage 1 is actually doing the read from the database. So it's not only getting the current state, but it's also getting the version corresponding to that particular set of keys. And then this is then fed into stage 2. So stage 2 is getting 2 pieces of data. One is the versions corresponding to the keys from stage 1, and then it's also getting the actual events from the microbatch. And then that's doing the work of discarding away things that are not that are equal to or below the version, and then only doing the aggregation on the remaining. And then that's the delta that we feed into stage 3, and then stage 3 is also getting the current state from Cassandra from stage 1, and so combined together, stage 3 can now reliably count them both together, aggregate them both together, and then write it back to the database, and then finally the commit can do what it was doing before. So in this modified version, now have we solved the overcounting problem? Well, let's start with stage 1. Again, stage 1 is doing reads, no side effects, nothing at all. Not a whole lot different from the previous version we had. So safe. Again, stage 2, no big deal. No reads, no side effects, perfectly safe. Stage 3, so back to how we were doing it before. So we could do kind of partial writes and then fail on it. But now, when we do that, the ones that have not been updated, the versions are also not being updated for those particular rows. And so if the application crashes, comes back, and then the data gets fed in back again, the version numbers for those which have not been updated yet will be the previous version number that we have. But for the ones that have been successfully updated in stage 3, we're actually going to get the updated version numbers, which means stage 2 is now going to discard the versions corresponding, I mean, the data corresponding to those. And so we are not going to anymore overcount in stage 3. So stage 3 is now kind of, or the pipeline as a whole is not going to kind of overcount under this failure mode. And likewise, with the final like commit failing, same idea. Only difference is that, yeah, we'll basically be discarding all the data from the previous microbatch in this particular case. So if that's all the data that comes in again, then we are basically going to go do 0 updates to the database at that point. All right. So far, I mean, we've been talking about like addition, like adding the number of clicks, stuff like that. But the real thing is that this doesn't have to be limited to just additions or even simple mathematical operations. Aggregation logic in general is actually now residing in the pipeline. So all these deltas are being computed in the pipeline, which means you have complete control over what that logic is. So it can be arbitrarily complex. It can be like richer data set, like data structures. It could be arbitrarily anything that you want to compute. As long as you have a well-defined aggregation function, you could basically carry out any kind of operation here. So that kind of generalizes the idea and lets it apply to a lot more use cases. And in terms of what's next, or some ongoing work, I mean, given the generalization aspect of it, like one of the things that we are kind of working on, or at least implementing at this point, are windowed joins. So again, joins could actually be treated as a specialization of aggregation, just because joins are nothing more than kind of merging together a few different kinds of or pieces of data together. And the advantage we would have, as opposed to using the traditional join mechanisms or whatever is already provided by the processing engine, is that now you can have arbitrary business rules as far as joins are concerned. So essentially, things like if you had, like, let's say 3 different streams are coming in, and you're trying to join events across those based on a key, it's possible that maybe 2 of them have the key while the third one doesn't. And your business logic may require maybe that, oh, I want all 3 of them to actually have a key for me to successfully emit something. But there might be other scenarios where it's like, oh, I'm OK with these 2 streams having data. Even if the third doesn't have it, I'm perfectly fine with still emitting an output. So things like that actually now can be performed because now we have arbitrary control over what the aggregation process is. And another aspect they're also kind of working on is deduplication as part of the aggregation framework. More so because typically when you have data being published to Kafka or in general, like any kind of publisher side of story, these publishers are not typically idempotent. And so the input streams could end up having duplicates from the previous processing pipeline. Which actually will be impacting the current pipeline because the aggregation is now getting the same data more than once, but we are not going to kind of dedupe that out by default because we are not looking at the keys that make them duplicates. We are actually looking at the the primary keys. And the primary keys, wise, we have already solved this problem, but deduplication is still needed for the input data itself. So that's another thing we're kind of looking into in terms of, or at least implementing in terms of having that as part of the aggregation step, because that's where it actually has an impact. So with that, just some closing remarks. I mean, yeah, just wanted to throw out there, we are hiring across a wide set of skill sets. And so please do check out the careers page if you're interested in learning about that more. And also, there's like a whole bunch of places you can look in terms of looking at our culture or just what we've been doing lately, stuff like that. So you could visit any of these and get some more information there as well. And thanks for listening. Thank you.
Maybe I missed this, but how do you deal with out-of-order data?
Sure. Yeah. The question is, how do you deal with out-of-order data? So just the way it's typically the case. I mean, essentially, you kind of you could define a window and then just throw things out beyond a certain point. I mean, for example, we are kind of collecting, for the most part, like the aggregates over as the day progresses. And so, yeah, we don't. The next day, you probably don't care about the previous day, and that's could be like a kind of a reasonable boundary at which you say, okay, any new data coming in after this point, we don't anymore bucket into the old day. We just kind of discard it. We filter it. So yeah, that's kind of that's something that happens on an earlier stage. I mean, so the aggregation isn't really going. It's going to kind of aggregate everything that comes to it. But then the initial ingestion stages basically would be the place where these kind of filters would be applied, where they would discard the data.
You talked at the beginning having Flink versus Spark streaming. How's your experience with using one or the other, and where has it helped you or hurt you?
Can you repeat that? Spark streaming?
I was saying at the beginning you said use Spark streaming and Flink, or you mentioned both of them. Have you worked with trade-offs between there for yourself?
Sure, thanks. So we started using Spark streaming like quite a few years ago, and Flink wasn't kind of at a point where it was mature enough, and so. Yeah, back then, Flink was not even a candidate among the ones we had considered. So a lot of the work that's been happening has been in Spark streaming, for that matter. I mean, we've kind of been expanding on that. In terms of Flink, I mean, like the team I belong to, or at least I belonged to until recently, like, yeah, we were completely in the Spark streaming world. But there are other parts of the organization that's kind of investing in Flink, and they're kind of working on that. But I guess the one aspect to it, I could say is that in either case, I mean, like the biggest problems or the biggest things that we had to build on were more around state management and the life cycle of state management. So that's basically where a lot of the things had to be built kind of outside of, or like kind of had to be strapped on top of these frameworks to kind of make sure that in a production use case, we kind of continue to kind of work over longer periods of time. So I think in that regard, they kind of have maybe not the same set of problems, but still state management is an issue. And I guess both are making improvements, and hopefully we'll see, Spark Summit is next week, and Flink Forward had, a few announcements from before. So yeah, hopefully we're hoping to see some more progress there, but otherwise, until then, we're kind of continuing doing it ourselves outside of the frameworks.